Okay, welcome back, and we're going to finish up Chapter 3. This is Section 3, Applications of Linear Programming. And so we're going to start off, we're going to be doing examples, and basically we're going to be applying everything that we've learned from Section 1 and 2 here. And so the biggest thing is going to be making sure you read the problems carefully, understand what's going on, and then set up your objective equation and your constraints appropriately and correctly. And then it's basically just graph and test the corner points and find the one that makes your objective function either maximum or minimum. So let's get started. Okay, so canoe rentals. Thomas Pinedo plans to start a new business called River Explorers, and he is going to rent canoes and kayaks. And so they're going to go down a 10 miles down the Clarion River in Cook Forest State Park. Now, here's the information that they give you about him starting his new business. He has $45,000. Okay, and that's what he has to buy canoes with. And so there's the $45,000, and he can buy canoes at the rate of $600 each, and kayaks are $750 each. The facility can only hold up to 65 boats, so that's another constraint, right? So the number of boats can only be 65 or less. The canoes he will make, the canoes will rent $25 a day, so that's the revenue he will bring in for the canoes, and the daily revenue is going to be $30 a day. And it says how many canoes and how many kayaks should he buy to earn the most revenue. So there's what we're trying to maximize, the most revenue, if all the boats are rented each day. So under the assumption that they all get rented. Okay. So here's the thing. We got to make sure we read these carefully because we've got information here. So the first thing we notice is that the amount of revenue, the total revenue that he gets is going to be $25 times the number of canoes plus $30 times the number of kayaks. So let's make canoes be X, and let's make the number of kayaks Y. And so the total revenue is going to be $30 times Y plus $25 times X. Okay, and that's going to be our objective function. The constraints is going to be the fact that the total cost to start the business to buy the boats has to be less than or equal to $45,000. And the amount of cost per boat is going to be $600 for canoes, each canoe, and $750 for each kayak. Okay, and the number of canoes and kayaks can't exceed 65. So with that in mind, we can set up this table here with all of the information that we need to set up a system of equations and also see what we need to maximize here. Okay, so here's our table, right? So X is the number of boats, right? X is the number of canoes. Y is the number of kayaks. So we know this sum has to be less than or equal to 65. Here's the cost of each boat, and we know this sum, right? 600 times X plus 750 times Y has to be less than or equal to 45,000. And then here's the revenue that we get for each boat. And so this is going to be our Z function or objective function. And so this is what we end up with. Now we can divide this by 150 like they do, because remember from our previous chapter that we can multiply an equation or an inequality by a non-zero number, and it won't affect the solution, okay, of the system for solving for X and Y. So this inequality reduces to this inequality, and so we get this one with this one that we get. And also remember, well, we want the number of canoes and the number of kayaks to be greater than or equal to 0. That goes without saying. So these are some constraints on the model, or constraints that weren't specifically mentioned but make sense, right? We don't want negative canoes and negative kayaks. Okay, so with these four inequalities, those would be our constraints. And of course, this is our revenue function, our objective function that we want to maximize. Okay, so here is what we get when we plot all of the constraints. So we know that we have to have this region bounded by this region right here, these sides. Okay, and so this is where the two equations here intersect, and then this is where they intersect. And again, this is your region, but you also still need to make sure that you have the correct region. And how are you going to do that? Well, use test point. Use a test point. So because it could be in between here, and it could be in between here, and it could be over here. So obviously, just make sure you use test points to find out which is which. Okay. Let's see here. So once we have once we do this, we have our points, right? Our corners, right? We find the corner values, the corner points, and once we have those corner points, we plug them into a table where we plug those points into our objective function and solve for z. And in this case, we just find the one that gives us the maximum value. And so this is 20. This is the point. So that means that to maximize revenue each day, assuming that you rent all the boats, 25 should be canoes and 40 should be kayaks. Okay, well, what about this one? Here's another example. This is where we have a 4-H member raises only goats and pigs. She wants to raise no more than 16 animals, including the fact that no more than 10 can be goats. Okay. She spends $25 to raise a goat and $75 to raise a pig, and she has $900 available for this project. Each goat produces $12 in profit, and each pig produces $40 in profit. Okay, it says how many goats and how many pigs should she raise to maximize total profit under these constraints. So we're talking about maximizing profit, so our z function or objective function is going to involve $40 times the number of pigs and $12 times the number of goats. So let's x be the number of goats and let's y be the number of pigs. Okay, and then we know that the total number of animals cannot be more than 16, so x plus y has to be less than or equal to 16. And then, of course, the number of goats, which is x, has to be less than or equal to 10. And then, of course, the cost, we have 25 times x plus $75 times y, and that has to be what? Less than or equal to $900, right? That's all the money she has. So if we take all of this and we put it together in a system, well, we get this, right? Here's our table. So number of animals raised has to be less than 16, and it's going to be number of goats plus number of pigs. And then the goat limit, that means the number of goats has to be less than or equal to 10. And of course, here's our cost, right? 25 times x plus 75 times y equals 900, or less than or equal to 900. And then here's the profit that we're going to maximize. Okay, so now, what we're going to do is we're going to take all of this information that we're seeing and we're going to plot these equations, right, just like we did in the previous sections, and then we're going to shade in the regions or use test points to find out which bounded region are we in, okay? And so once we know the bounded region, we test the corner points, okay? So here's our objective function. Here's the list of constraints that they have right here, okay? And so if we graph these, we find this, right? So we find that this bounded region here is the solution set. Then again, you can use test points. All you have to do is test a point in here and see if it satisfies all of the values, all of the constraints. Okay, and then once you do this, you set it. You find the points, right? So you find all of the intersection points, all of the corner points. Okay, so what we're going to do is we're going to take each of these points and we're going to test them in our objective function. Of course, the one that gives us the maximum value of z is the answer. Oops. So if we go back, here are the points, and we just plug in all the points, and we find that the one that gives us the maximum value is the one that says, hey, have all pigs and no goats. Okay, all pigs and no goats. Okay, and so if we look at this, look at z, so we look at the final value. Oh, did we do that? Hold on. So $480 is the maximum profit for this project. And so, let me go back. So here is the point. Okay, and we get z equals 480 at this point. And notice that we've got all these other values, but they're all lower than the maximum value in this region. Okay, now here, this is the main function. Okay, so notice that our z function at 0.12 gives us the maximum profit, but also look at this equation here, right? X plus 3y is equal to 36. Right? Goes through that same point, which is our, which one is that? That's our cost. Yeah, this was our cost function. Okay, notice that we took the cost and we divided by 25. Okay, which again, we can do that. So notice that we took the 25x 75y plus less than or equal to 900, and we just divided everything by 25, and this is the cost function that we got. Okay, and here's an example of this one. So if we look at this function, we notice that this function, right, gives us these values, and again, this is the maximum value between these two functions. Okay, and we can find the value here. Yeah, I think that's all I want to say on that one. Okay, and then the final example is we want to talk about rescue shelters, and we're talking about feeding animals. It says certain animals in a rescue shelter must have at least 30 grams of protein and at least 20 grams of fat per feeding. These nutrients come from food A, which is 18 cents per unit as far as cost, and has 2 grams of protein and 4 grams of fat per feeding or per serving, or per unit rather. And food B, which costs 12 cents per unit, has 6 grams of protein and 2 grams of fat. Now, food B is bought under a long-term contract requiring that at least 2 units of B be used per serving. Another contract requires that the amount of food B used be no more than 3 times the amount of food A that is used. Okay. So with all of this in mind, here are the constraints. So our constraints is 1, we have food A is X, and the number of units of B is Y. Now in this case here, they don't put a maximum value on it. Okay, so this is just X and Y, right? Now, the grams of protein, though, are restricted. So we can, each feeding can have 2 grams, 2 times the number of units of food A, as far as protein, right? 2 times the number of units of A, is 2 grams times that. So that's the total number of grams of protein from food A, plus the total number of grams of protein from food B. And so this amount has to be more than or equal to 30. Okay, hold on a second. Let me make sure that that's what they're saying. Yeah, at least, right? Must have at least and at least, right? Keywords. So at least 30, and then of course the grams of fat. So 4 units times the 4 grams times the number of units of A, plus 2 grams times the number of units of B. The sum of the grams of fat has to be at least 20 grams. Okay, and then the long-term contract says what? Says that Y, right, the number of grams of the number of units of food B has to be at least 2 units each day. Okay, and then of course we have the cost function. But there's also the fact that what it said that the amount of units of food B can't be more than 3 times the amount of food A. Okay, and so this is where we get this constraint right here. So Y has to be bigger than or equal to 2, but it cannot be more than 3x, which is 3 times the amount of food A. And of course, x has to be bigger than or equal to 0, right? We can't have negative amounts of food again. And of course, this is the cost. No, this is the amount of fat, and this is the amount of protein. Okay. Okay, so now we have our setup. And now we need to graph and then solve. And so in this case here, notice that it's an open region. Okay, again, you've got lots of closed regions. Make sure you use test points. Okay, and or solve it and just ask yourself, am I above the line or below the line? Okay, again, remember what you learned in section 1. Okay, so here we get this region. Okay, so now we've got to find all the points and see if there's a solution to this. So we can test these 3 points because these are the only corners. Okay, but that doesn't mean that there's necessarily a solution. But we could, if it is, we'll find it at one of those 3 corners, and then we could see, what happens here. So here we go. So now the thing is remember the question. What are we trying to do? We're trying to minimize the cost function. Okay, we want to minimize the cost. So now we don't have to worry about all this over here because we're moving this way towards the origin, right? So we're going to test these 3 points, see which one gives us the minimum value. Okay, maximum value, it goes on forever because remember they don't put a constraint on the amount of food, right? So let's test these 3 points, and when we plug those into our objective function, we find that the minimum cost is this one right here, which happens when you have 3 units of food A and 4 units of food B, and that's your mixture. So then here's the cost. Okay, so if you have 3 units of food A and 4 units of food B, you're going to have the minimum cost that will also make sure that the animals are getting their proper nutrients. Okay, and that's it for this chapter. Again, make sure you review, do the exercises in the textbook at the end of each section. Do the review exercises at the end of the chapter. Practice the other examples in the textbook, not just these. Definitely redo these and make sure you know how to do these, but also there's other examples in the textbook. And then most importantly, make sure you watch this video before we cover it in class, and make sure you have all of your questions all of the problems that you're getting stuck on, because we're going to work through them all and make sure that you understand what's going on. So again, be prepared and ask lots of questions, and let's work through this. Okay, have a great night, great day, great afternoon, whatever the case may be, and I will see you next time. So this is the end of Chapter 3. Next time we'll start Chapter 4. Thanks and goodbye.